just what is string theory? What are these strings?
String theory is an attempt to make sense about all the phenomena we see in nature in terms of one unified field theory. So 20th century physics basically understood reality, or as much as we know of reality, in terms of two big theories. It unites the quantum mechanics that describes the atoms and molecules with general relativity, which describes stars, planets, and galaxies. And of course we have to unite them somehow, because the stars, galaxies, and the planets are ultimately made out of atoms. So it wouldn't make sense to have one theory that only works for atoms, while another theory entirely would be used for stars and galaxies. They're all made out of the same stuff, so they have to be described by the same theory.
How did we get from the atom to the string?
Before string theory, there were elementary particles, lots of them, electrons, muons, and quarks. And to just try to convey the idea, I'll just draw a little dot, which is meant to symbolize a point particle. And as I said, there are lots of them, electrons, muons. Some of them better known to the public, some less. Like maybe you haven't heard of towels, but in my line of work, they're important beasts. Now in string theory, instead of a point particle, you've got a loop of string. But it can vibrate in many different ways. This is one shape it can have. It could be more like a circle, or it could look wavy. And the different shapes the string can take, according to string theory, are the reason that there's so many different kinds of particles. The different particles are just different ways a string could vibrate. But let's just imagine it from the point of view of someone who maybe isn't a physicist but appreciates music. So where does the beauty of music come from? Well, a violin string or a piano string can vibrate in many different ways, just like one of these. And in that case, the different kinds of vibration are associated with what we call the different harmonics, or higher overtones. If you had only the pure tone, that would be the sound made by a tuning fork. And you know, to the human ear, it sounds very harsh. The beauty of music comes from the higher harmonics, which give music its richness, and which are the reason that we've got both violins and pianos. So, just like the beauty of music, so the richness of the string comes from the fact that the string can vibrate in many different ways, leading to all the different particles and forces that we see in the universe. In fact, that's also the way we would combine the quantum world, which involves all these particles, with gravity, which from this point of view, Einstein's theory involves one more particle, which is the graviton, or the basic unit of Einstein's gravitational waves.
So these vibrations of these strings can unite the two clashes that we have between quantum mechanics and gravity?
If this theory actually pans out, then the way it works is that the graviton and all these other particles, which we see in the subatomic world, come from different ways that this string could be vibrating.
Now you said something interesting, if it pans out.
Yes.
Is that a big if?
Well, it's of course a big if, because like anything else in science, it isn't in the bag until it's actually in the bag.
Well, when's it going to be in the bag?
Well,
right now it's a bag of tricks. When is it going to be real,
I don't know, of course, about the future, but it's interesting to look back at the past, because the trail started in the late 60s, when the first glimmerings of string theory appeared in efforts that physicists were making to understand the strong interactions among protons and neutrons. Mm-hmm. So it's been a long trail of discovery since then, full of surprises. And in each decade we've learned that the way we understood the theory a decade before was very naive. Then physicists stumbled onto this new framework where there were a lot less theories that were possible, and they all involved gravity. So instead of general relativity being impossible in the standard framework, it was necessary in this new framework.
And that's a good proof then.
Well, that's a very good encouragement that it's on the right track,
yeah.
And it certainly was the single most important thing in getting me excited.
Mm-hmm.
So it's great to have a theory that forces you to have gravity instead of the old framework where gravity was impossible.
And weren't there 5 possible theories for string theory?
The traditional viewpoint back in the 80s was that there were 5 possible string theories, which was a big improvement over physics as it had been before, because in the standard quantum mechanical framework, there are all kinds of theories you could have, in fact, infinitely many of them. What we learned in the 90s was that the different string theories, as we'd known them traditionally, were actually different aspects of one bigger theory. It's a little bit as if one string theory described the tusk of the elephant, one described the tail, one described the elephant's ears, and another described the trunk. And then finally in the 90s we learned that what we've been studying from different points of view were different aspects of one elephant. It's a very dimly lit elephant, we don't understand it very well, but at least by now we know that there's just one elephant, one candidate for superunification of the laws of nature, which we've been studying from different points of view for so long. So there's a picture that's often drawn to illustrate this, where the different string theories that existed traditionally are the corners of this plot. I'm actually drawing 6 corners. There were 5 string theories. One of them is the heterotic string, heterotic E8 times E8 technically. And then there are the other string theories. I won't bother with their names. And there was a wild card that entered this mix that isn't really a string theory. But what we now understand is that there's this one elephant, this one theory, M theory, which we don't understand too well, but it's our candidate for superunification. And the different string theories, as we had them traditionally, are different limiting cases of this one richer and still mysterious theory.
Why call it the M theory?
If we really knew what it was, we'd give it a better name that described it better. But since we don't really know what it is, we give it a temporary name like M theory. I always say that M stands for magic, mystery, or matrix, according to taste. Magic and mystery are clear enough, and matrix is a mathematical ingredient that's used in describing the theory.
What kinds of experiments or how do we look for these strings to prove that the theory is right?
What we're really hoping to find in accelerators are what are called the superpartners of the ordinary particles. Supersymmetry, which is this fascinating new concept in physics that emerged because of its importance in string theory, predicts a lot of new particles that should be discovered at accelerators in the coming years. Maybe at Fermilab if we're lucky. Fermilab is the big accelerator near Chicago, and otherwise probably in Europe at the Large Hadron Collider.
Does supersymmetry tell us anything about that mysterious dark matter in our universe?
Astronomers see in the universe that if you look at a galaxy, it seems to be surrounded by a cloud of invisible matter that we don't know what it is. We just call it dark matter because we don't see it. So supersymmetry makes a fascinating implication that one of these supersymmetric particles that we hope to discover in accelerators has just about the right properties so that the dark matter could very well be a cloud of these almost invisible supersymmetric particles. The idea is that this dark matter cloud envelopes the whole universe, the whole galaxy I should say, including our solar system. So they're passing through the Earth, through our houses, our bodies all the time, for the most part not interacting because they couple so weakly to ordinary matter.
Well, how would you know if you found one if you don't know what
Well,
you're really looking for? Right? Or do you know what you're
we know
looking
what we're looking for. They would have a big underground tank. They put it underground to shield it from ordinary cosmic rays. There are a lot of particles that come from space all the time. Some of the most important elementary particles were first discovered in cosmic rays. You'd like to shield yourself from all the conventional cosmic rays. Then you go underground, you've got this underground tank, and every now and then an atom will suddenly heat up because it's been scattered by one of these dark matter particles. So we'd like to directly observe that, and to really know what's going on, we want to produce the same dark matter particles in accelerators and study them in a controlled fashion.
As someone who's been covering physics for 20 or 30 years, I'm always impressed with the obsession that physicists have in explaining the Big Bang. What was there before there was the Big Bang?
So, of course, we don't know an answer to this question. What was there at the beginning? Who started the clocks? It sounds like a paradox, but understanding it better is part of what we'd like to know. And if I could just give you a hint about what an answer might look like, I certainly can't do more than that.
Go for it.
Let's just think that nowadays we don't have any trouble telling time. We just look at our watch and see that it's 4:15. And time seems like an obvious concept. But in the 20th century, a lot of things that seemed obvious turned out, when you look more closely, they're not so precisely defined. So 100 years ago, it seemed like a particle had a definite position and velocity. But then with quantum mechanics, it turned out that that was fuzzy. And now, with more modern thinking, we can see that if we could try to combine quantum mechanics and gravity, the notion of time gets fuzzy. So this fuzziness won't really matter in everyday life, because we just don't tell time accurately enough for this slight quantum mechanical fuzziness to matter. But as you went back toward the Big Bang, the quantum mechanical fuzziness would become more and more important. I probably speculate that near the Big Bang, the notion of time really breaks down. And so the question of what was the beginning and what was there before the beginning, that kind of question will ultimately turn out to not quite make sense.